Hello future engineers, welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to share my videos to your friends and to your friends' friends. That's one way you can keep me going, inspired and refreshed. Now if you find my videos interesting and important to your studies, also please don't forget to subscribe. So here is a portion of distributed forces. So you must first master derivation of formulas for volumes, areas and arcs or lines, and also familiar with them. And this part will be to enhance your thinking skills, especially in locating centroids of volumes, areas, and arc lines, which are necessary later in analyzing a system with distributed forces. Level 41. Use integration to compute the z-coordinate of the centroid of the half cone. So here's the figure, and let's have our slab parallel to this semicircular end area or region as shown in the figure. So the distance of the plane of this uh, semicircular disc is y from the xz plane, and the thickness is dy. The radius of this semicircular slab is z, and imagine that z is revolved about the y-axis, so everything will be z from the figure. So it may also be x, but I just call it z because this one is parallel to the z-axis, and imagine that it is revolved about the y-axis, but z is equal to x also. So volume is integral of differential volume, and differential volume is area of the semicircle pi over 2 radius square z square times thickness dy. So volume equals integral of dv, and dv is pi over 2 z square dy. So limit should be from 0 to r for y, from 0 to r for 0 to h rather for y. So from the figure, by similar triangles, z as to y equals r as to h. So that means z is r over h times y. Substitute, volume equals pi over 2, integral from 0 to h of r over h times y, quantity square dy. So simplifying, volume is pi r square over 2h square. Then the integral of y square dy is y cubed over 3 from 0 to h. So volume is pi r square over 6h square, quantity h cubed minus 0 cubed. So the volume is pi r square h over 6. Then applying Varignon's theorem, volume times z sub z equals integral of g sub c dv. Volume times z sub g, rather, the z coordinate of the centroid of the entire half cone, equals integral of g sub c dv, where g sub c is the location of the centroid of this differential element, which is a semicircular disc. Since this is area, then the location of the centroid of a semicircular disc or semicircle is the same as that of a semicircle, which is 4 times radius over 3 pi. And since the radius is z, it is 4 times z over 3 pi. So g sub z is 4 radius, which is z over 3 pi, just like the centroid of a semicircular area. Substitute, so volume pi r square h over 6 g sub z equals integral from 0 to h of 4z over 3 pi times pi over 2z square dy. Simplifying, cancel pi, then we have 2/3. Then the value of z is r over h times y. So pi r square h over 6 z sub g is 2/3 integral of r over hy quantity cube dy. So pi r square h over 6 z sub z is 2 r cube over 3 h cube. Integral of y cube dy is y to the 4th over 4 from 0 to h. So pi r square h over 6 z sub g is equal to r cube over 6 h cube, quantity h to the 4th minus 0 to the 4th. So simplifying, the right side is r cube h over 6, then cancel out r square h, then we'll have r left here divided by pi. So g sub z is r over pi. So that's it for this problem. Level 42, determine the centroidal z coordinate of the curved surface of the half cone by integration. So here's the figure. This time, let's locate the z coordinate of the centroid of the surface. So it's the lateral surface of this cone. So just this part. So therefore, our strip should be a surface also, as shown. So this is the surface, and its distance from the xz plane is y. The radius would be this one, parallel to the z-axis. So it's z, then z also, radius. And that's why then thickness is dy. The variable of integration is y, but the surface have this slanted differential element which is denoted by ds. So that you can view it, let's draw the top view. So this is the top view. We have here the strip which is z. Then this thickness is dy along the y-axis, but along this slant height it is ds from the figure. So that distance is y, this is r, and the whole of this distance is h, but this slanted element is ds as shown. So that the surface area is ds times the length of this semicircular arc, which is pi times radius, pi times z. So surface area is integral of differential surface area, and differential surface area is ds times the length of this path, which is circumference of a semicircle, pi times radius, or pi z. So that's it for surface area. Length ds times the length of that arc or path, which is pi times z. So ds from the figure, z from the figure is by similar triangles, z as to y equals r as to h, but ds as to dy, slanted element as to this dy, is also the ratio of this slant height of this right triangle. The hypotenuse of this right triangle is square root of h square plus r square, then as to that distance, which is h. So ds therefore is square root of h square plus r square divided by h times dy. Then z as to y equals r, big R as to h. So z is r over h times y. So substitute into this formula, and limit should be from 0 to h, because the variable of integration is y. So 0 to h of ds, which is square root of h squared plus r squared over h dy, then times z times pi z pi times z. Simplifying, surface area is pi r square root of h squared plus r squared over h squared. Then the integral of y dy is y squared over 2 from 0 to h. So simplifying, cancel h, because this is h squared, cancel h squared. So the surface area is pi r square root of h squared plus r squared over 2. So pi r square root of h squared plus r squared over 2, that's the surface area. Then by Varigdon's theorem, surface area times z sub g is equal to the integral of g sub c, the differential surface area. Now g sub c is the z coordinate of this differential element, which is a semicircular arc. And remember, the centroid of the semicircular arc from its base, from the diameter, is 2r over pi, where r is the radius of this arc, which is in this case z. So therefore g sub c is 2 times z over pi, 2r over pi. Take note of that. Remember the location of centroids, which were derived in the preceding parts of centroids, of volumes, areas, and lines and arcs. So pi r square root of h squared plus r squared over 2, z sub g is integral of quantity 2 z over pi. Then differential surface area is this one, square root of h squared plus r squared over h dy, then pi r over hy. So simplifying, cancel pi, so we have in the right side, you just copy the left side. The right side would be 2r over h squared. So pi r over 2, after we cancel square root of h squared plus r squared. So 2r over h squared, integral from 0 to h. Z is ry over h. Then we have y dy left in this part. So pi r over 2 z sub g is 2r squared over h cubed. Integral of y squared dy is y cubed over 3 from 0 to h. So simplifying, g sub z is 4r over 3 pi h cubed times h cubed minus 0 cubed. So after we cancel r, then cross multiplies, so we have 4, 2 times 2, 4 over pi. This is 3h cubed, so that's why we have 3 pi h cubed. So simplifying further, cancel h cubed, so we have g sub z is 4r over 3 pi. So that's it for this problem. By method of composite volumes, determine the centroidal coordinates of the volume. So by inspection, the composite volumes is symmetric with respect to the x and y axis, and the centroid lies on the z axis. Definitely it is symmetric with respect to the z axis rather. So therefore barred x, or x sub g equals y sub g equals 0. So for the solution, let's tabulate everything here, and we know that xg equals yg equals 0. So call this element 1, element 2, then element 3. There are 3 elements or objects here. So xg equals yg equals 0 as anticipated. So we only need g sub g. So we have element, the volume in cubic mm, the g sub c of the individual element in mm, and the product volume times g sub c in mm to the fourth. So for element 1, the volume is pi 2 to 125 square. The radius is half of 250, 125 square times height 475. So using your calculator there, pi 125 square times 475, that's 7421875 pi. Then G sub C is half of 475, 237.5. Then the product volume times G sub C is the value here, 176269513 pi. For element 2, the volume is pi radius square times height. So the radius is half of 450, 225. So pi times 225 square times 325. And that is 1645312 pi. G sub C is 475, which is this, plus half of 325. 475 plus 325 over 2, that would be 67.5. Then the product of volume and G sub C, put it here, 3.2952 times 10 to the 10. Then for element 3, the volume, because this is a cone, pi radius is 225 again, pi 225 square times height 400 over 3, pi r square height over 3. So pi times 225 square times 400 over 3, that's 212,05750.4. G sub C is 475 plus 325, that's 800 plus 1/4 of the height. Remember, the centroid of a solid cone is 1/4 of the height from the base. So 475 plus 325, 800 plus 1/4 of 400, 100, so 900. Then the product, put it here, 1.9085 times 10 to the 10. Then for the sum of the volume, that's the sum, and the sum of this column here, volume times G sub C, 5.75747 times 10 to the 10. The value of G sub G therefore is this sum, volume G sub C divided by volume. So 5.75747 times 10 to the 10 divided by 96211,275, and that is 598.4 mm. Level 44, the composite body shown is formed by removing a semi-ellipsoid of revolution of semi-major axis h and semi-minor axis a over 2 from a hemisphere of radius a. Determine, letter A, the y-coordinate of the centroid when h is a over 2, the ratio h over a for which yg is negative 0.4a. So remember that for a hemisphere, the volume is 2/3 pi radius cube, while for hemi-ellipsoid or semi-ellipsoid, the volume is 2/3 pi radius, which is a over 2 square, times b, which is in this case h, and h is a over 2. So it's the same thing, 2/3 pi for hemisphere, 2/3 pi a cube, that's the volume. For ellipse, 2/3 pi, supposedly radius square times h, in this case a over 2 square times h. So volume of hemisphere, 2/3 pi a cube, while the volume of ellipsoid is 2/3 pi a over 2 square times h, and h is also a over 2. So volume of ellipsoid is 2/3 pi a over 2 square times a over 2. So simplifying, volume of ellipsoid is pi a cube over 12. So the net volume is volume of hemisphere minus volume of ellipsoid. So 2/3 pi a cube minus pi a cube over 12. Factor out, so that if you simplify, that's 7 over 12 pi a cube. By Varignon's theorem, 7 pi a cube over 12, yg is equal to volume of semi-ellipse 2/3 pi a cubed times negative 3/8 of a, the centroid. Remember, 3/8 of a. So minus volume of ellipsoid pi over 12 a cubed. Then the centroid is negative 3/8 of h, where h is a over 2. So negative 3/8 of h. So it's the same as that of ellipsoid. The radius of ellipsoid is a, but in this direction, the radius in that direction is h, and h is a over 2 for ellipsoid. So cancel pi a cube. So 7 over 12 yg equals negative h over 4, negative a over 4. Then this is positive a over 32, 64. So a over 64. Simplifying the right side, we can now compute yg. So yg is equal to negative 45a over 112. Then for the second part, the ratio h over a, for which yg is negative 0.4a. So volume of ellipsoid this time is, let's use this general formula. It is 2/3 pi a over 2 square times h, or pi a square h over 6. So volume is volume of ellipsoid minus volume of volume of semisphere minus volume of ellipsoid. And if we factor out pi a square over 6, then we have 4a minus h. So that's the volume, net volume. Then Varignon's theorem, volume pi a square over 6 times quantity 4a minus h times yg, which is negative 0.4a, equals volume of hemisphere times negative 3/8 of a minus volume of ellipsoid pi a square over 6 h times centroidal z coordinate of semi-ellipsoid is negative 3/8 of h in general. So cancel out pi a square and simplify. 4a minus h over 6 times negative 0.4a equals, we have negative a square over 4, then plus h square over 16 after we cancel pi a square. Then distribute, we have negative 4 over 15 a square plus negative h times negative 0.4a over 6, that's ah over 15 equals negative a square over 4 plus h square over 16. So h square over 16 minus ah over 15, then negative a square over 4 plus 4 over 15 a square is a square over 60 equals 0. The LCD is 240. So multiply everything by 240 to have coefficients. So that would be 15h square minus 16ah plus 4a square equals 0. So applying the quadratic formula, h is negative of b, negative of negative 16a. So h is 16a plus minus square root of negative 16a square minus 4 times a 15 times c 4a square all over 2a, 2 times 15. So simplify the radical, h is 16a plus minus 4a over 30. So if we use plus, 16 plus 4a is 20a over 30, so that's 2/3. If we use minus, so we have 16a minus 4a, 12a over 30, that's 2/5 of a. So h is 2/5 of a. If we use minus, if we use plus, h is 2/3 of a. So therefore, the ratio h over a is either 2/5 or 2/3. So h over a is 2/5 or h over a is 2/3. So that's it for this problem. Level 45. For the machine element shown, locate the x-coordinate of the center of gravity. So for the solution, let's consider this big rectangular parallelepiped as element 1. This this element with semicircular section has element 2. Then this one to be removed, element 3. Then element 4 for this rectangular parallelepiped. Element 5 for this triangular wedge. So volume 1, along X the dimension is 38, 19 times 2. Along Y it's 10. Then along Z it's 90. So volume 1 is 38 times 10 times 90. So 3,4,200 mm cube. Then the X coordinate is 19, half of 38 along X. So take note, we are just required to locate the X coordinate of the center of gravity. So XC1 is 19 mm. Volume 2 is area of semicircle pi times 20 square over 2 times thickness, which is 10. So volume 2 pi times 20 square over 2 times 10, and that is 2000 pi mm cube. Then X sub C2 of the element is 38. Then the distance from the base or from the diameter to the centroid of semicircle is 4r over 3 pi, where the radius is 20. So it is equal to XC2 is equal to 38 plus 4 times 20 over 3 pi, and that is 46.488 mm. Volume 3 is to be removed, so negative pi radius 12 square times height 10. So pi, negative pi 12 square times 10, that's negative 1440 pi, and the distance of the centroid is simply 38. XC3 is 38. mm. Then volume 4, volume of rectangular parallelepiped along X 10, along Y 30, not 40, because we only consider up to here. We already considered this from volume 1. So the height is 40 minus 10, so 30. And along Z it's 24. So volume is 10 times 30 times 24. And that is 7,200. Then X sub C4 is half of 10. So 5. Then volume 5 is 1/2 of, so 19 minus 10 is 9. So the base is 9. The height is 30. And perpendicular to the, or in the Z direction, 24. So volume 5 is 1/2 of 9 times 30 times 24. And that is equal to 3,240. Then X sub C5 is 10. Since the base of the triangle is 9, so 10 plus 1/3 of 9, and that is 13 mm. So XC5 is 10 plus 1/3 of 9, so 13 mm. So by Varignon's theorem, let's compute for the volume, net volume, 3,4,200 plus 200, 2,000 pi minus 1,440 pi plus 7,200 plus 3,240. So the volume is 46399.3 mm cube. Then by Varignon's theorem, 46399.3 xg is 3,4,200 times 19 plus 2,000 pi times 46.488 plus negative 1,440 pi times 38 plus 3,240 plus 7,200 times 5, then plus 3,240 times 13. So from there we can now solve xg, and xg is equal to 18.28 mm. So that's it for this problem.